Welcome to Everyday Mathematics. Today we move forward to part 2 of the 2025 Columbia University Integration B qualifying round. And today we'll be looking at the last 14 problems, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. So these 14 problems are the subject of today's integration. We'll try to go through them fast and furiously, and I hope this may benefit you. So if you haven't subscribed to our channel, we do really encourage you to subscribe to our channel. If you like what you're seeing, please stop and like. If you would like to share what we're doing with somebody you think may benefit from this, please go ahead and do that. Without much ado, let's jump in and start on the integration. Problem, the important thing to do here is I can rewrite the numerator as the derivative of a quarter x to the 4 minus 1, right? All over x to the 4 minus 1. And what we find here is we can pull that constant out, and still in the numerator we have x to the 4 minus 1 differentiated over x to the 4 minus 1, right? Since we know that if you're integrating the derivative of a function fx over fx, when you integrate this, you get the natural logarithm of fx plus integration constant. So using this formula, what we find here is that we have a quarter natural logarithm of x to the 4 minus 1 plus the integration constant. Some people might write a quarter ln for natural logarithm of x to the 4 minus 1 plus the integration constant. Both these are okay, and that was our answer. Number 12. What we like to do is first factorize whatever is in the denominator. So we have 1 to infinity x minus 1 over, we'll x out, we have x to the 4 minus 1. And this is the same as since we could also further factorize whatever is in the denominator into x squared minus 1, x squared plus 1. Difference of two squares, right? And then we can further factorize this part here, so that now we have 1 to infinity x minus 1, x minus 1, x plus 1, x squared plus 1, right? And we see that this and that could cancel away, so that now we have integral from 1 to infinity of 1 over x times x plus 1, x squared plus 1. When we may want to now express the integrand into a partial fraction formalism, and how I would want to do it is I would want to focus on these two parts first. So I would pull 1 over x out and then say, okay, I have 1 over x plus 1 times x plus 1, x squared plus 1. So let's express this into a partial fraction, and we're going to it as follows. Let's learn how to express this as a partial fraction, right? So the rule of thumb is that we express the numerator as a 1 degree less than the denominator. So we have a, which is a constant, over x plus 1, and then bx plus c over x squared plus 1, right? So that now we can rewrite and say 1 is equivalent to ax squared plus a, and this comes when you recombine this fraction, plus bx squared plus bx plus cx plus c. Now we see that a plus b here consists of the constant next to the x squared term, and since we don't have a corresponding constant on the left hand side beside the x squared term, we'll say that a plus b equals to 0. And then the b and c, b plus cx doesn't have a corresponding constant on the left hand side, so we say b plus c equals to 0. And then obviously a plus c here has a corresponding constant on the left hand side, which is equals to 1. So here we see that a is equals to negative b, and here we see that b is equals to negative c, and from that we see that this would mean that a plus a is equals to 1, which means that a equals to a half. Meaning that now from here, we see from this aspect, we see that b is equals to negative a half and c is equals to a half. So with that in mind, that means that now our fraction 1 over x plus 1 times x squared plus 1 is the same as a half times 1 over x plus 1 minus a half x minus 1 over x squared plus 1, which we can re-express as a half x plus times x minus 1 minus a half x over x squared plus 1 plus a half 1 over x squared plus 1. Okay, so our integral now from 1 to infinity of 1 over x in bracket 1 over x plus 1 x squared plus 1 is the same as integral 1 to infinity 1 over x, and then we plug in this, so we can actually pull a half out, so we have 1 over x plus 1 minus x over x squared plus 1 plus 1 over x squared plus 1, right? And so this is interesting because now we have a half out here, and now we have 1 over x plus 1 minus 1 over x plus 1 plus 1 over x times x squared plus 1, right? So we can express this as a partial fraction, and continue with the process, okay? We've brought it to this point where we have 1 over x times 1 over x plus 1 minus 1 over x squared plus 1 plus 1 over x times 1 over x squared plus 1. We can re-express this into further partial fractions. So we have 1 infinity. This is the same as 1 over x minus 1 over x plus 1. This is an easier partial fraction. It's very easy to really figure out that. And 1 over x squared plus we have 1 over x minus x over x squared plus 1. So we can now combine these two so that we have half to infinity 2 over x, and then we have 1 over x plus 1 minus 1 over x squared plus 1 minus x over x squared plus 1, which becomes now half 2 natural logarithm of x here, natural logarithm of x plus 1 here, arctangent of x and here natural logarithm half natural logarithm of x squared plus 1 to infinity. So we could actually do a couple of things here to make things easy, and that way we say half log of x squared over x plus 1 times the square root of x squared plus 1. So we've combined this, and that, minus the arctangent of x, 1 infinity. So limit as x tends to, so let's rewrite whatever we got. So we have half natural logarithm of x squared over x plus 1 square root of x squared plus 1 minus the arctangent of x, 1 to infinity. And this is the same as half limit as x tends to infinity of the natural logarithm of x squared over x plus 1 square root of x squared plus 1 minus limit as x tends to 1 of the natural logarithm of x squared over x plus 1 square root of x squared plus 1 minus, in bracket, limit as x tends to infinity of the arctangent of x minus limit as x tends to 1 of the arctangent of x. Okay? As you can see here, it's very easy to see that the numerator and the denominator kind of diverge at the same rate. So we could go ahead and try L'Hopital, but to me that I see to be heading to 0, because the log of 1 is going to be 0, minus as x tends to 1, so we have log of 1 over 2 times the square root of 2, right? And then minus pi over 2 is this minus pi over 4. Okay, and so right, so that is correct. That is correct. So we come to half positive if we take things out. So we have log of 2 root 2 minus pi over 4, and we can actually maybe even express it more succinctly, because this is same as log of 2 3 to the power 2 minus pi over 4, and this can come over this side. So our problem now becomes a half log of 2 3 to the 2 minus pi over 4, which is a half 3 over 2 log of 2 minus pi over 4, which we can succinctly express as 3/4 log 2 minus pi over 8. And so the problem we had, which was the integral from 1 to infinity of x minus 1 over x to the power 5 minus x, is equal to 3/4 natural logarithm of 2 minus pi over 8. And that, ladies and gentlemen, was the answer that was expected. So on to problem number 13. This is actually very easy and tractable. So the definite integral from x equals to 1 to x equals to e of the natural logarithm of x times x plus 1 over x. So I'm used to writing natural logarithm of x as just log of x. Okay, so let's just assume that that is what I would be meaning going forward. So this is 1 to e of log of x, x plus 1 over x. And this would be 1 to e x log of x plus 1 over x log of x, right? This is the same as 1 to e log of x times the derivative over half x squared, right? Plus log of x times the derivative of log of x, meaning that, okay? And so quickly, we can now use integration by parts. And integration by parts, we say if you have a product of function v and the derivative of function u, when you integrate that, you have uv minus u times the derivative of v. So that in mind, we now are going to say that this is a half x squared log of x 1e minus 1 to e a half of x squared times 1 over x, right? So this covers this entire guy. But here, this is very easy to see that we have a half log squared of x 1 to e, right? So we're differentiating the square of log of x. Now with that in mind, let's continue and see how we may be able to solve this. So we say that our problem now is a half x squared log of x 1e minus 1 to e half x squared 1 over x plus a half log squared x 1e, right? And this becomes limit as x tends to e over half x squared log of x minus limit as x tends to 1 over half x squared log of x, right? Minus integral 1 to e of, actually half, we can pull half out, of x plus limit as x tends to e over half log squared of x minus limit as x tends to 1 of log squared half log squared of x. As we can see, log of 1 tends to 0, so this tends to 0. This also tends to 0, right? And then here we have half e squared, since log of e is just going to be 1, minus this guy here now becomes a quarter x squared 1 to e plus a half, because log of e is 1, squared is just going to be 1. So this becomes a half e squared minus a quarter e squared plus a quarter plus a half, which now, based on this, we get a quarter e squared plus 3/4. And that is the answer that was being sought out. This is a very interesting problem, right? The definite integral from x equals to 0 to x equals to 2 power the square root of 1 minus sine squared of x. So here we can say this is the same as the same integral from x equals to 0 to 2 pi of the square root of 1 minus sine squared x is the same as cosine squared of x, right? So let's leave it there, because if we go and assume that the square root of cosine of x is going to be equal to, of cosine of x squared is going to be equal to cosine x, we may land onto catastrophic ground. So let's plot this thing out, right? So we have 0, pi over 2, pi, 3 pi over 2, and 2 pi. Cosine of x is just going to be equal to something like that. This is cosine of x. And then the square of that is going to be equal to, this is cosine squared of x. The square root of that is going to be slightly elevated, goes to 0 there, and then slightly elevated, then goes there. But we see that the area of this lobe is the same as the area of this lobe, same as the area of this lobe, same as this area of this lobe. So we have 1, 2, 3, 4, right? And we can now say that the integral from 0 to 2 pi of the square root of cosine squared of x is the same as 4 times the integral from 0 to pi over 2, the integral of cosine x, which is equals to 4 sine of x from 0 to pi over 2, so which is the 4 times sine pi over 2 is 1 minus 0, which is equals to 4. And that is the answer that was expected. So this is a very interesting problem as well. Integral from x equals to 0 to x equals to pi over 6 of the fourth root of cosine the fourth x minus cosine 2x. So we can rewrite this in a easy manner. So we have cosine for x, and then we can write cosine 2x as cosine squared of x minus sine squared of x to the power quarter. So knowing that sine squared x is the same as 1 minus cosine squared of x, which we quickly get that we have 2 cosine squared of x here minus 1 quarter, which is 0, pi over 6 cosine 4 of x minus 2 cosine squared of x plus 1 to the power quarter, right? And this is the same as cosine squared of x minus 1, yeah, squared, right? And actually we could, now that I see it, so we had come to a point where we have integral from 0 to pi over 6 of cosine of x squared minus 1 squared to the power quarter. Since this guy is less than 1 for the most part, unless we got 1, this is how we may want to write it. 1 minus cosine squared of x squared quarter, which is the same as the square root of 1 minus, because this becomes sine squared of x. Okay, and so we could just say, okay, that's the same as the square root of sine squared of x, so the square root of sine squared of x, because the 2 here and a quarter multiply, you get a half, and so we have 0, pi over 6, the integral of sine of x from 0 to pi over 6. Okay, so integral now becomes 0 pi over 6 sine of x, right? And this is same as cosine of x, 0 to pi over 6, which is the same as negative cosine pi over 6 minus cosine of 0. This is 1 coming from this, negative, minus cosine of pi over 6 is going to be root 3 over 2. And so our big integral from 0 to pi over 6 of the fourth root of cosine to the fourth of x minus cosine of 2x is equals to 1 minus root 3 over 2. And that was the answer expected. This is also an interesting problem, and it's kind of challenging, but I think it's easy. We could separate this from the negative side and also the positive side. So we say this is the integral from x equals to negative 10 to 0 of x squared over e to the x plus 1 plus from 0 to 10 of x squared e to the x plus 1. So let's focus on that for a minute, and we say that let x be equal to negative u or vice versa, meaning that we can substitute for dx with du. I'm looking at what we have here. This integral becomes 10 to 0 u squared over e to the minus u plus 1 negative, and we have du. This negative here allows us to flip things around so that we have the limit, so that we have integral from u equals 0 to 10 of u squared of e to the negative u plus 1 du. So we will box this for now, and we say that our main integral now becomes integral from x equals to 0 to 10 of x squared 1 plus e to the negative x plus x squared 1 plus e to the x. This part we've derived from here. Okay, so let's continue from here. So our integral now has become integral from 0 to 10 of x squared of 1 plus e to the x plus x squared of 1 plus e to the x dx. If we multiply ex both the numerator and denominator here, we get the problem becoming 0 to 10 of x squared e to the x over 1 plus e to the x. Okay. And when we sum things up there, we get x squared pulled out, and we have ex plus 1 in the numerator, 1 plus ex. These would cancel. So our problem now has become the integral of x squared from x equals to 0 to 10, which becomes, so since we have 0 to 10 integral of x squared, we have x cubed over 3, 0 to 10, which is 10 cubed over 3, So in other words, integral from -10 to +10 of x squared over e to the x plus 1 is equals to 10 cubed over 3. And that, ladies and gentlemen, was the answer that was being sought for. Is an interesting one. The definite integral from x goes to 0 to x tend to infinity of 1 over x squared plus 1 times x to the fourth plus 1. The first thing that I always try to see is when I see an x squared plus 1 in the denominator, I don't really even bother so much. I don't try it. And also if I see the infinity here, I always think about substituting with tan theta. So we'll say let x be equal to tangent of theta such that dx d theta is equals to sec squared theta, meaning that we can substitute for dx with secant squared theta d theta. So let's box that, right? And then when x equals to 0, what that means is that tangent of 0 is going to be theta will be equal to 0. When x tends to infinity, theta tends to pi over 2. Okay, and that means that our integral now 0 to infinity of 1 over x squared plus 1 x to the fourth plus 1 is same as 0 to pi over 2 of 1 over tangent square theta plus 1 tangent to the power theta plus 1 times sec square theta d theta. So since tan squared theta plus 1 is the same as sec squared theta, we have 1 over sec theta times tangent the power 4 theta plus 1 times the theta d theta. And we see these cancel, right? So our problem has essentially reduced to 0 to pi integrated over tangent to the power 4 theta plus 1. And this can be re-expressed as 1 over sine to the power 4 theta over cosine to the power 4 theta plus 1. And so this is 0 pi over 2 cosine to the power 4 theta over sine to the power 4 theta plus cosine to the power 4 theta. Okay. Important thing to note here is now we're going to use a symmetry relation here, right? Let's see. So we say that our problem is 0 to pi over 2 cosine the fourth over cosine to the fourth plus sine to the 4 theta. Let's say let phi be equal to theta minus pi over 2 such that d phi equals to d theta, right? A small change in phi is a small change in theta. Then our problem becomes negative pi over 2 here, 0, and then we get cosine of phi plus pi over 2, since we can take it that to the power 4 over cosine to the fourth phi plus sine to the 4 phi plus pi over 2 d phi. What we see here is cosine phi plus pi is the same as negative of sine phi, but we are taking to the power 4, so we still get sine phi to the fourth over here we get sine to the 4 phi plus, and here we're going to get cosine 4 phi. And then since our problem now has become sine to the 4 phi over cosine to the 4 phi, I've probably interchanged whatever is in the denominator, but the order really doesn't matter here at this point. When we substitute the negative in the phi, because we are powering to the fourth, we're only left with the negative from the d phi here, right? And then that negative allows us to now reverse the limit. So we have 0 to pi over 2 sine phi over cosine. So this result is actually very important because what it tells us is that the result we've gotten is that I being equal to the integral from 0 to pi over 2 of cosine to the 4th theta over cosine 4th, theta instead of phi, sine squared theta is the same as 0 pi over 2 sine squared sine 4th theta over cosine to the 4 theta plus sine, this is the power 4 theta. And so 2i is equals to 0 to pi over 2 of cosine of the 4th theta plus sine to the 4th theta over cosine to the 4th theta plus sine to the 4th theta, which is equals to 0 to pi over 2 of 1, integral of 1, which is theta, 0 pi over 2, which is pi over 2. So I definitely is equals to pi over 4. Okay? So what this is telling us is that the integral from 0 to infinity of 1 over x squared plus 1 times x to the 4th plus 1 is equals to pi over 4. And that was the answer that was expected. This integral, number 18, the indefinite integral of 1 over square root of x plus 1 plus square root of x can be attacked in the following manner, can be solved in this way. So we can multiply both the numerator and the denominator by square root of x plus 1 minus x, square root of x plus 1 minus square root of x, such that in the numerator we have square root of x plus 1 minus square root of x over x plus 1, difference of 2 squared minus x. This cancels, so we have essentially that. Okay, and so this is the same as 2 over 3 x plus 1 to the power 3 over 2 minus 2 over 3 x 3 over 2 plus the integration constant. And that is our answer. Okay. Problem number 19, the indefinite integral of 2x times the arcsine of x squared. I think it will be fun to just substitute by saying let u be equal to x squared such that du dx is equals to 2x, meaning that we can use du to substitute for 2x dx. And so our problem 2x arc sine of x squared becomes the integral of arc sine of u du. Well, we could further say let y be equal to arc sine of u such that sine of y is equals to u, and cosine of y dy du is equals to 1, meaning that we could use cosine y dy to substitute for du. And so our problem now becomes, in place of arc sine of u, we have y, and then we have cosine of y. And for du, we have cosine y dy, which is the same as integral of y times the derivative of sine of y. And we can use integration by parts, where we say if we have v times the derivative of capital U, which is same as u v minus capital U derivative of v integrated. So this is the same as y sine y, because this is our u, this is our v, minus the derivative of our u is derivative of y with respect to y, which is 1. So and then we have the derivative of, this is v, so we're just going to have sine y here, which is equals to obviously y sine y plus cosine of y plus c. We are not going to stop there. We're going to go back stepwise up to what x was. Okay, so we got our answers: y cosine of y sine of y, y sine of y plus cosine of y plus c. But we had said that let y be equal to the arc sine of u. This was something we had said previously, so this means that we have arc sine of u for y here, and sine of that, so we have u plus square root of 1 minus sine squared. So this cosine y is the same as 1 minus sine squared y square root, right? So it means that here we are going to feed in u squared plus c. But also we had said that u be equal to x squared, right? So the final answer is now x squared arc sine of x squared plus square root of 1 minus x to the 4th plus c. Therefore, the integral of 2x arc sine of x squared is equals to x squared arc sine of x squared plus square root of 1 minus x to the 4 plus c. Some people might want to write it as x squared arc sine of x squared plus whatever floats your boat. And that is the answer. So this problem number 20, is actually an easy one, because we could rewrite the problem as x plus 1 minus 1 over x plus 1, right? And we see that this is the same as x plus 1 over x plus 1 minus 1 over x plus 1. So then that cancels, so we have integral of 1 over x plus 1, which is the same as x minus the natural logarithm of x plus 1 plus the integration constant. Some people may want to write it as that plus 1. Okay, and that is it. Also an interesting problem. We'll just solve it in a fast way. The definite integral from x equals 0 to x equals to 1 of the natural logarithm of x plus 1 over x squared plus 2x plus 1. So what we're doing there is 0 plus to 1 of the natural logarithm of x plus 1 over x plus 1 squared dx. We could just say let x be plus 1 be equal to u, meaning that du dx is equals to 1, and therefore we can use du to substitute for dx. And what that means is that when x equals to 0, u equals to 1. When x equals to 1, u equals to 2. So we have ln of u of u squared du, which means that we could just say this is 1 to 2 ln derivative with respect to u of 1 over u du. Use integration by parts. If you have v du as same as uv minus u dv. Okay, integration by parts. So going forward to just say, okay, so our problem is 1 to 2 u derivative of 1 over u du, the same as 1 over u natural logarithm of u 1 2 plus 1 to 2 1 over u times 1 over u. This negative has interacted with the minus, so we have a positive here. So which is the same as 1 over 2 on the upper side, natural logarithm of 2, minus 1 over 1, so this is just 0, natural logarithm of 1, plus 1 over u squared is just going to be equal to 1 over u, 1 to 2. So this becomes negative 2 plus minus a half plus 1, which is equals to a half minus and so what we are seeing here is that if we have integral from 0 to 1 of the natural logarithm of x plus 1 over x squared plus 2x plus 1, that is equals to a half 1 minus natural logarithm of 2. Okay. Problem number 22, the definite integral from x equals to pi over 2 to x equals to negative pi over 2 to x equals to pi over 2 of e to the power 1 minus 1 over cosine squared x over cosine squared x. So this is the same as e to the power 1 minus sec squared of x over cosine squared of x, which is the same as e negative sec squared of x minus 1 times sec squared of x dx, because 1 over cosine squared x is same as that. And so we come to pi over 2 to pi over 2 e to the power tangent squared of x times sec squared of x. So let u be equal to tangent of x, which means that du dx is equals to sec squared of x, which means that we can substitute for sec squared dx with du. As x tends to negative pi over 2, when x tends to negative pi over 2, that means that u tends to negative infinity. As x tends to positive pi over 2, it means u tends to positive infinity. So our problem becomes from negative infinity to positive infinity of e to the power u squared du, so which is the same as that Gaussian integral. And that was the answer expected. So what is a flow function? Because this is what is being asked here. We're having a definite integral from x equals to 0 to x equals to 2025 of the flow of the square root of x. So if you have the flow of fx, that is equals to k when fx is less than k plus 1, is between k plus 1 and greater or equal to k, such that if we have the flow of the square root of x, that's equals to k when the square root of x is less than k plus 1, greater than k. Therefore, x will be greater than or equal to k squared and less than k plus 1 squared. What this means is that if we have that to be the square root of x, from 0 to 1, we're going to just have 0. That's the integer less than that. From 1 to 4, it jumps up, and so we have it to be 1. As soon as it hits 4, it jumps to 2. So 4 to 9, all the way to 9. And so we're going to have this discrete regions. So this is 0 to 1, 1 to 4, 4 to 9, and so on. And we see that in those regions we have discrete values 1, 2, all the way up to the square root of 2025, which I'm thinking is 45. But we see from 45 onwards, there is nothing. That is our limit. So our problem now becomes a summation from k equals to 0 to k equals to 45 minus 1, which is 44. And we are integrating from x equals to k squared to k plus 1 squared. And in those intervals, k equals to 1, k plus 1 squared is 4, and so on. So in those intervals, the value is just k, right? So this is the same as k to 0 to 44 of kx, k squared, k plus 1 squared. And so this is the same as k 0 to 44 of k k plus 1 squared minus k squared. So difference of two squares, we get 44k times so difference of two squares, we're going to sum and then we're going to subtract. So 2k plus 1 times 1, okay, which is equals to summation from k equals to 0 to 44 of 2k squared plus 2k, and so one important thing to notice, so our problem has come to the summation from k equals to 0 to 44 of 2k squared plus k. But we know that if we're summing from k equals to 0 to n of k squared, we have n plus 1, 2n plus 1 over 6. Summing of k from k equals to 0 to n, that's the same as n plus 1 over 2. So with that in mind, we come to here, n is 44, so we have 44 times 45. 2 times 44 is 88, plus 1 is 89 over 6 times this 2 plus, we have 44 plus 45 over 2. By 1, 1, by 2, 1, by 2, 3, by 3, 1, by 3, 15. Let's delete that. By 2, 1, by 2, 22. Okay, so we have 44 times 15 times 89 plus 22 times 45. Okay, 15 times 89, which is 58, 740 plus times 45 is 990. 58, 740, which is equals to 59, 730. And that is the answer. So this is an interesting problem. Looks a little bit convoluted, but one thing we may want to do is let's pull the 2 out so that we have x to the 6 plus 4 over, let's pull the x out in the numerator, we have x to the 6 minus 2, and we could now go further and re-express this as x to the 6 minus 2 plus 6 over x to the 6 minus 2, which is equals to 2 x to the 6 minus 2 over x to the 6 minus 2 plus 6 x to the 6 minus 2. So this and that would cancel, so we have 2, 1 over x plus 6 over x to the 6 minus 2. So we can rearrange things a little bit here. So we have 1 over x plus 6 over x. So x to the 6 could be expressed as x to the 3 minus root 2, x to the 3 plus root 2. It's one way we could express that, and so this becomes 2, 1 over x plus 6 over x, and we have 1 over x cubed minus root 2 minus 1 over x cubed plus root 2, and we realize that we have to put a 2 root 2 here, so that when we have root 2 minus root 2, it becomes 2 root 2, and to cancel that we have this here. So our problem has become, so we have 2, and then we have 1 over x, and we have plus 6 over 2 root 2 x, and we have 1 over x cubed minus root 2 minus 1 over x cubed plus root 2. So this is 2, 1 over x. We could say 3 over root 2, and we have 1 over x, x cubed minus root 2 minus 1 over x, x cubed minus root 2. Okay, so this is 2, 1 over x plus 3 over root 2, and we can say this is 1 over x. This x squared, right, over x cubed minus root 2. So when this goes up, when multiplying by x squared, so we have x cubed, and so what that means is we have negative root 2 there divided, and here we have the same thing, 1 over x minus, so there is a plus here, sorry, 1 over x cubed plus root 2 over root 2. And there's an x squared here. Apologize. Okay, so what we see is that this root 2 here would interact with this, and this also would interact with that. And so we have 2, 1 over x plus 3 over 2. And this negative here means that we can swap things around. So we have x cubed over x cubed minus root 2 minus 1 over x minus 1 over x plus x squared, and this is x squared, sorry, over x cubed plus root 2. Okay. So our problem becomes 2, 1 over x plus 3 over 2. And we've said now we have x squared over x cubed minus root 2 minus 2 over x plus x squared over x cubed plus root 2. So we have 2, we have 1 here, and we have minus 3. So we have 3 x squared over x cubed minus root 2. There is 1 over 2 here plus 3x squared. Have 2 there, x cubed plus root 2. And minus, since this interacts with that, negative 3, so we have 2 over x, which is the half can propagate out, and so we have, interestingly, 3 over x squared, x cubed minus root 2 plus 3 squared x cubed plus root 2 minus 4 over x. So this becomes log of x cubed minus root 2 plus log of x cubed plus root 2 minus 4 log of x. So the log here is just natural log. Okay. And so this becomes natural logarithm of x to the 3 root 2 x root 2 minus 4 log of x plus c. So this is log of x to the 6 minus 2 minus log of x plus c, which is log of x2 divided by x to the 4 plus the integration constant.